I'm so sorry we have to do the lectures this way. There's so much more to being able to meet in person and get all your questions. That was very nice for this class, such a small class. Do email me as you have questions. I'm going to try and catch us up as best we can. We're a week behind. I'm going to go a little fast tonight. I'm going to go a little fast in general because the videos have to be short. There's a memory limit for what I can do, but I'll put what lectures I can online here, and I'll put up notes, and you can work with those. I hope that'll not discourage you from learning this stuff. It's very important material. Today we're going to continue what we were doing with vectors. We're going to talk about the dot product. And the dot product is actually a very simple thing. This is from Paul's online math notes, by the way, just for today. You can Google that and come up with these pages. Click on Calculus 2. It's a 3-semester course they have there. This is near the end of Calculus 2, and you can find these notes in the write-up. And then I'm going to also refer to our textbook quite a lot and assign some problems out of there. But this has a nice write-up on it. So if I have two vectors, A with components A1, A2, A3, and B with components B1, B2, B3, I can take the dot product, a very simple thing. You'd never think this would be useful, would you? A1, B1 plus A2, B2 plus A3, B3. It's just this times this plus this times this plus this times this. We call that the dot product of the two vectors. Why would it be called a product? It's part sums and part products. We'll see shortly as a calculus result. Actually, it follows the product rule when you take derivatives of vector-valued functions, and other things like that behave like products also. It also distributes over addition, which you'll see today. Alright, so there is reason for calling it a dot product. Interestingly, the dot product of two vectors is not even a vector. You take the product of numbers, you get a number, you think product of vectors ought to be a vector, right? Well, there'll be another one called the cross product where that's true. But the dot product of two vectors is actually a number. It's this number times this one plus this one times this one plus this one times this one. Just pairwise. Very simple. How could that possibly be useful? We're going to find out. Sometimes the dot product is called the scalar product because the output is a number, a scalar. It's also an example of what's called an inner product in higher mathematics if you study that. Alright, so here's the simplest thing you can look at. What's nice about these notes is you can click on and see the solution on a lot of these. Look at this. Here's V and here's W. You can also do this with vectors of length too. It's just, and we've written them here in the IJK notation. This is just alternate notation for this one. This is like the vector bracket 5 comma minus 8, vector bracket 1 comma 2. So it's just a different notation than that one, recall. If I take these two vectors and dot product, the dot product will be 5 times 1 plus minus 8 times 2. Easy as that. And you can click on here and say, show the solution. And there it is. V dot W is 5 times 1 minus 8 times 2 is minus 11. So try these at home. This is kind of a nice resource. There are other good resources too, but this is kind of nice because you can click on some problems and check your answers. Here are some properties of the dot product. One reason it's a product is it distributes over addition. U dot V plus W is U dot V plus U dot W. It has the distributive property. It also has the commutative property of multiplication, right? V dot W is W dot V. And here's an interesting one. V dot V is the length of V squared. We can look at that one separately. Let's do a proof of that just to show a simple proof of one of these. For instance, if I take, let's do vectors of length 2 here, vectors in the plane, so that they only have two components, V1, V2, dot, W1, W2, and what is the definition? It's this times this plus this times this, V1, W1 plus V2, W2. So then what is the dot product of a vector with itself? V dot V is actually equal to, well, if these are both V's, it's V1, V1 plus V2, V2. Is V1 squared plus V2 squared is the square root of V1 squared plus V2 squared is the length of V squared, right? Remember, the length of a vector is the root sum square of its components. We did that last time. That was essentially the Pythagorean theorem. If you have a vector in the plane, let's put it at the origin. It doesn't matter where it is, but if it's in the plane, it goes to the point V1, V2, and it's V. And this side's length absolute value v2. By the Pythagorean theorem, this side squared is this squared plus this squared, and so the length of v, the length of this side, is root v1 squared plus v2 squared. That's how we define the length, also called the norm or magnitude of a vector last time. So this is an important property of the dot product, that vector dotted with itself is just its length squared. Alright, so there's a proof of that one, and we can do some of these other ones too. Let's do one more just to make this, show you how easy this is. You don't want to see all of these, you want to see a couple of them so you get the flavor of doing this, and you feel like if you get stuck, you can figure some of these things out. Suppose I took v dot w plus u. I want to prove the distributive property. Well, what is that? It's v1, v2 dot. Remember how to add vectors? You add them component by component. So the vector v plus w has components v1, w plus u is w1 plus u1, w2 plus u2. That's the sum of those two vectors. And now if I dot these, it's this one times this one. v1 times w1 plus u1 plus this one times this one. v2 times w2 plus u2. And now you can rearrange those as v1 w1 plus v2 w2. Just put them in a different order, multiply them, put them in a different order, plus v1 u1 plus v2 u2. And now this one is the dot product of v with w, so it's v dot w. And this one is v dot u by our definition up here, plus v dot u. And there's the proof of the distributive property. v dot w plus u is v dot w plus v dot u. Dot product distributes over addition of vectors. Alright, well, we also have a whole algebra of vectors. The zero vector is the vector whose components are all zero, and v dot any zero vector is the zero vector. He's missing a little arrow on the top there. Oh, I'm sorry, not. Is the number zero. And if v dot v equals 0, then v is the zero vector, because after all, v dot v is its length squared. If the length of a vector is 0, then it must be the zero vector. So you can do all sorts of proofs like that. So it says the proofs are mostly computational, so we'll just do a few of those there. Let's look at this then. There's also a wonderful geometric interpretation to the dot product, as he points out here. Suppose you take an angle between two vectors, theta. You have the following theorem, which, again, I'll omit the proof. It's in a lot of trigonometry books, not just here. But with a bunch of geometry, you can show that a dot b, the dot product of two vectors, is actually equal to the length of a, the length of b, times the cosine of the angle between them. That's the foundational important property of the dot product that makes it so useful. This helps you to determine the angle between two vectors, right? I can, if I have a dot b is length of a, length of b, cosine of the angle between them, I can use that to find the angle between any two vectors. Let's go back here and erase some of this. Oops. This one. Got the wrong thing. So now, we have the theorem. One of the most important ones for the dot product is that for any two vectors, v dot w, and this isn't just in 2 dimensions, it's in any number of dimensions. V dot W is the length of V times the length of W times the cosine of theta, where theta is the angle between them. What is the angle between them? There's a choice, right? If here's D and W, maybe it's this angle, because you want to go counterclockwise. Maybe it's this angle. Maybe you want to go the other way, clockwise. What is it? The angle between them is the smaller of these two angles, measured in the positive direction. So this is theta here. This one here, the one angle between 0 and 180. And then they have this fundamental relationship. And we say that's important because now, given any two vectors, you can solve this for theta by dividing by length of V, length of W, and get cosine theta is equal to V dot W over length of V, length of W, and then theta is an angle between 0 and 180 degrees, right? So is the inverse cosine. If I take the inverse cosine of both sides, I get theta is the inverse cosine of V dot W over length of V, length of W. This always works as long as neither of these are the zero vectors, so you get a division by 0. So you can find the angle between any two non-zero vectors by this formula now. Let me do a short example of that. Suppose I said, find the angle between, this is my favorite example for angle between, V equals 1, 3, and W equals minus 1, 2. What could be the angle between those vectors, do you think? Alright, if you drew them in the plane, alright, these vectors have two components, so they're plane vectors. One of them goes up here to the point 1, 3, if it's run at the origin. The other one that goes over, shorter, sorry. Goes over here to the point with coordinates minus 1, 2. Notice I'm using round braces for coordinates of points and angle braces for vector components. That's how you can tell that I'm looking at a point or a vector. Now what is this angle between these two vectors? Well, according to this formula here, we have that theta is equal to the inverse cosine of V dot W. Well, that's this times this plus this times this. 1 times minus 1 plus 3 times 2, there's V dot W, over length of V, length of W. Well, the length of these is the root sum squared of their components. So the length of this one is square root of 1 squared plus 3 squared. And the length of this one is the square root of minus 1 squared plus 2 squared. So now we have that theta is the inverse cosine of, let's see, minus 1 plus 6 is 5 over square root of 1 squared plus 3 squared, that's supposed to say, is square root of 10. Square root of 1 plus 4 is square root of 5. It's this inverse cosine. Well, you can simplify that as the inverse cosine of 5 over 5 square root 2 if you rewrite that. The 5's cancel. Evidently theta is the arc cosine of 1 over square root 2, also known as the square root 2 over 2. You remember that one, right? That's 45 degrees. We usually use radians here when we're dealing with angles. So we'll say the angle between them is pi over 4. There is the angle between those two vectors computed with the formula. Alright, so this is one of the nice things about geometry. It actually, in higher mathematics, is used to define what we mean by an angle between vectors. there's something in there, right? It looks like it. This is how you make it rigorous. All right. Now, here's the proof of it. You can use the law of cosines, that the length, if you draw the triangle with A and B, and the vector A minus B, remember, goes between their endpoints. Remember that from last time. The length of this third side of the triangle, by the law of cosines, is this side squared plus this side squared minus 2 times this side, cosine the angle between them. That's the law of cosines. When you solve the law of cosines, you get down to this result, which shows that actually A dot B is length of A, length of B, cosine of the angle between them. You don't have to do that for the test. It also works in 3 dimensions. Here's another problem here. Determine the angle between these two vectors in 3 dimensions. The 2-dimensional case, you could actually draw a triangle and probably figure it out, but boy, in 3 dimensions when it's tilted, you got to find the plane they lie in and re-get their coordinates in the plane. That's terrible, but the dot product makes this easy. Look how we do this. A dot B is this times this plus this times this plus this times this is minus 22. Length of A is root sum square of these is square root of 26. Length of B is root sum square of those is 29, square root of 29. And so cosine of the angle is the dot product over length of A, length of B. Comes out to be minus 0.8 something. Theta, the angle between them, is the arc cosine. That number is about 143 degrees in this case. So this is very useful in all sorts of physical applications, as you might imagine. Now here's an interesting result. What if length of A dot B is equal to length of A, length of B? That means the cosine between them is 0. They're parallel. So if you find that property, then you know they're parallel. We're also going to make another definition here. Just looking for it on the page. Here we go. This will be a definition. 2 vectors are said to be orthogonal if their dot product is 0. But what does their dot product mean? So this will be a definition. Touching that with my hand. Vectors VW in any number of dimensions you can imagine, and taking 4-component vectors and doing 4-dimensional space. All the mathematics works just perfectly, even if you can't visualize it. This is what's very fun about it. You can do imaginations in higher dimensions. Vectors V and W are said to be orthogonal. Dot product is 0. What does that mean? V dot W equals 0 by our theorem is equivalently length of V, length of W times the cosine of the angle between them is 0, is equivalently by the 0 product property, either this is 0, in which case if its length is 0, the vector is 0, or this is 0. If the length of W is 0, that's equivalent to saying the vector is 0, or the cosine of theta is equal to 0. But how can the cosine of an angle be 0 that's between 0 and 180 degrees? Only if it's 90 degrees, right? Pi over 2 radians. So 2 vectors are orthogonal if and only if at least one is a 0 vector, or the angle between them, if they're non-zero vectors, is pi over 2. So that's what orthogonal means. It means either they're the 0 vectors or they're non-zero vectors that are perpendicular. So orthogonality encompasses the idea of perpendicularity. We'll just say vectors are perpendicular. Includes the 0 vector is then perpendicular to every vector. Let's should put arrows on here. Either V is the zero vector, W is the zero vector, or theta is 90 degrees. Now you can say something additional too. This is kind of a nice thing. A dot product's so easy to compute. What if I get a dot product that's positive? Suppose V dot W is positive. What does that tell me? That tells me that length of V, length of W, cosine of the angle between them is positive. But these are lengths. They can't be negative. If this product is positive, none of these can be zero, so it must be that these are positive. Which also means then that cosine is positive, right? These are non-negative, and they aren't zero, the product could be zero. So they're positive. That makes cosine positive. But if cosine is positive, what do you know? Theta is an angle between 0 and 180. That means you're in the first quadrant. So the dot product being positive is equivalent to saying that V and W are non-zero vectors with angle between them in the first quadrant, acute. Similarly, if V dot W is negative, what do you know? This is equivalently length of V, I should have put first just to be consistent. Length of W, cosine of the angle between them is negative, but these are non-negative. If you don't get zero, they must be positive. That means that cosine must be negative. But cosine negative for an angle between 0 and 180 degrees means you're in the second quadrant. You have an obtuse angle. So we have these three cases. The dot product can be zero, in which case the vectors are orthogonal. Either they're perpendicular non-zero vectors, or at least one of them is a zero vector. Or, if the dot product is positive, they form an acute angle, or if the dot product is negative, they form an obtuse angle. That's a very nice geometric observation. So here's some problems here. Determine if the following vectors are parallel, orthogonal, or neither. Parallel means that A dot B is length of A times length of B. The angle between them is 0 or 180. Just put 0 over 180 on that. So parallel means they're the same direction or opposite direction. They're along the same line. And then orthogonal means their dot product is 0. And usually they're neither, right? But here's solutions to this one. You take the dot product of this one with this one, you get 0, that means they're orthogonal, right? You take the dot product of this one. This one, 1/2 times, 2 times minus a half plus minus 1 times a fourth, gives you minus 5/4. That's a negative number. That means it's an obtuse angle between them, and they're not parallel or orthogonal. And then finally, in the last case, you compute their lengths. You find out their dot product is equal to the product of their lengths. Actually, minus that, I'm sorry. So it's 180 degrees between them in that case. They're parallel. And I need to correct this. A dot B is length of A, length of B, if the angle between them is 0. And it's minus length of A, length of B, if the angle between them is 180. All right. Here is a major help in that the dot product provides is projections of vectors. If I have two vectors and I want to take the projection of one on the other, imagine a light source out of infinity dropping light rays perpendicular down onto this vector here. It'll make a shadow of this vector that looks like this. We call this the projection of vector B onto vector A. It can also go this direction. It can project in the opposite direction of A. How can we compute that projection, right? This is actually very important in calculating work in physics and engineering, as we'll see later in the section. Well, we can do this following proof. to show that actually the projection of any vector b onto the vector a is a dot b over length of a squared a. So the projection of one vector onto another is an important concept for breaking vectors into pieces like that is used in things like work and also in Newtonian mechanics and all sorts of calculations. You want to find what portion of the rocket's thrust is pushing it forward, which is trying to make it turn. Use this kind of computation. You have to calculate projections. We can do these projections using the dot product. All right. Let's do an example here, and then maybe I can prove the projection theorem. I call it a theorem. Actually, it's a definition. We just make this definition, but there's a reason why, and I'll show the reason why. Suppose I want to find the projection of this vector onto this vector. We can do this in any number of dimensions. Let's look at the solution. We take a dot b, we take the length of a squared, and we say the projection of b onto a is a dot b over length of a squared a. And so we just compute a dot b was 4, length of a squared was 5, a is in this direction. So what happens is this is always a number that tells you how to scale a vector. You always get a vector in the direction of a, right? We're finding the projection of b onto a, so we get a vector parallel to a always, and it's this number times a tells you the projection of b onto a. So apparently it's 4/5 of a. It's pointing in the same direction, but 4/5 of the length of a. And here's the projection right here. Alright, let's try the proof of that just quickly, or the derivation of that, not the proof. Why would it be that that would be the projection? That always bugs me when I see something like that I use so much, and I don't know why the formula works. I hated that in physics. I never knew whether what I was doing worked because I didn't know where it came from, how to derive it, so I became a math major. Then we never did anything useful. We just always did theoretical equations. It was hard to marry the two courses together, actually. Hard to find mathematics that actually could solve a problem. Hard to find physicists that would actually prove anything they did. All right. So suppose I have this vector. Oops. This vector A, and I want to do its projection onto vector B. I want this vector to be the projection of A onto B. What do I do? Well, this is supposed to be dropping in perpendicular. And we have that, what is the length of this? This is the angle between the theta. If you remember from trigonometry, this side times the cosine of the angle is equal to this side, right? This side must have length of the hypotenuse times the cosine of the angle here. That's from trig, so the